Hi, it's Mr. Zachary, and we are looking at question number 24. Here's my picture of it. This is point A, point B, point C, point D, point E, 50 centimeters up. And so, looking at it, at point A, it's asking what's the gravitational potential energy. Well, it's mgh at A, and we know the height at A, but we don't know the mass. And sometimes that's okay. We can say that the gravitational potential energy is 5 times the mass, whatever the mass is, and the units for energy are joules. So it's m times 5 or 5m is the gravitational potential energy at point A. It's a little strange because normally you just get a number, but if you don't know the mass, that's what you have to do. Now, B asks, what's the kinetic energy at point B? Well, we know the kinetic energy is this, but what is the velocity at B? So we look and we say, if nothing's interfering, then the total energy at A is the total energy at B. And there are three possibilities of the types of energy it could have at A, types of energy it could have at B, but which ones does it actually have? And so we look and we can say, well, at A, it only has gravitational because no movement and no spring at all. And at B, if we make that our height 0, which we kind of have by making this 50 centimeters, we know that there's no gravitational, there's no spring still. So we get that the um, gravitational at A is equal to the kinetic energy at B. So m times 5, which we found up here in A, is equal to 1/2 times m times vb squared. Now both of these have m in them, and so if that's the case, mathematically, what you can do is you can just cancel out the masses. You can divide by m, and that cancels them out. And so you get an answer that the velocity would be 3.3 meters per second once you do the algebra. Now, the next question, C, is asking, well, how high will it go on the other side? Well, because nothing's interfering, the total at A is the total everywhere. It's just it could be different types of energy. At A, there's only gravitational potential energy. There's no velocity. So when you get over to the other side, at C, you're still going to have some velocity, and we know that at the highest point, the velocity has to be 0. So all of that energy would have to be turned back into gravitational potential energy. So if I have I'm making up this number, but if I have 100 joules of gravitational potential energy here, then I can only have a total of 100 joules anywhere in this, and if some's kinetic, then some is not gravitational potential. And so D is the highest point because by the point D happens, all of the energy is turned back into gravitational. There's no left for kinetic. And it can't ever reach E because that would require it to have a more total energy than it has at A. And that can't happen. Now, the next question says, what if it was moving at A? So now, not all of the energy at A is gravitational. Some of it is kinetic energy, which means the total you could actually get, you have more energy than you would before. And so you could get higher on the other side. How much higher? Or what would your velocity be at B? Sorry. The total at A is the total at B. Types of energy that they could have, and there's no spring, so I just left it off. There's no gravitational at B because you're at a height 0. Put in my numbers, and notice again, m, m, and m. So you divide by m on both sides, and you get that those cancel out. You get a velocity of 3.74 from that answer. Now in E, it asks how high will it go? Well, more energy at point A, so it has more energy than stopping at point D, so it'll go higher. So it'll reach point E because by that point all of it will have turned into gravitational potential energy. and F, you know that this is the energy that you put in. It is m times 5 joules. That's that gravitational potential at A. The energy out, if it only went up to 45 centimeters on the other side, the energy out would be the mass times 4.5 joules. So energy in is mass times 5, and the energy out is the mass times 4.5. So if we do the efficiency as being however much out divided by how much you put in, then I get 0.45 times the mass divided by 5 times the mass. Oh, I believe I put that in wrong, but I think the answer is still 90%. That's still 90% efficient to get the energy back out.